Hello everyone, I'm Alan Owens, GCMS Senior Product Specialist here at Shimadzu Scientific Instruments, and I'll be your moderator for today's webinar. But before we get started, just a couple of notes for everyone's viewing. There are a few items in the webinar console. Each of these items on the screen can be expanded by clicking and dragging from the bottom right of each window. If you're like me, you might accidentally close the screen and wonder where it went. At the bottom of the console, there's a widget bar that will open any of the windows you've accidentally closed. In that widget bar from left to right, first, you'll see a yellow question mark. This is for help if you experience any technical issues during the webinar. Next, the blue projector screen is the presentation window. The red film strip next to that is the media player. The purple Q&A is our question box. If you have any questions throughout the presentations, go ahead, type your questions in the box, and submit them. At the end of the presentation, we'll be answering the questions you submitted during both our panel and QA sessions. The other blue box is the speaker bios if you want to know more about us. And finally, the green paper is going to be our resources list. In here, you'll find links to both Shimadzu Scientific Instruments and Peak Scientific, the slides from today's presentation, and many other documents pertaining to hydrogen versus helium. Feel free to download these at any time throughout the presentation. If you're just now joining us, then welcome to the latest Shimadzu Scientific webinar, Helium versus Hydrogen, Lifting Your Chromatography Above the Rest. My name is Alan Owens, the moderator for today's webinar, and in this webinar, we will discuss some of the considerations and requirements necessary for a successful and acceptable switch. We will also cover the necessity of alternate carrier gases, including how it affects your chromatography. Also joining us today from the Philippines, discussing the benefits of hydrogen generators, is Ed Connor, who works for product management for Peak Scientific. We have an information-packed webinar today that we look forward to sharing. All links and resources are available for download in the resource section. As we proceed through the webinar, feel free to submit those questions at any time, and we're going to dedicate as much time as we possibly can afterwards to answer those for you. Fear not, if your questions are not answered, all questions will be answered post-webinar. With that, I'd like to introduce both Rick Karbowski and Kyle Reddick, GCMS and GC Product Specialists here at Shimadzu, and I will invite them to take it away. Kyle, honor is all yours.
Thank you, Alan, and thank you, everybody, for joining us. The first thing I'd like to start out with is the age-old economics supply versus demand debacle that we're really seeing here, which is making us interested in switching from helium to something that's a little bit more cost-effective. So the way that helium is actually gathered is through a fracking process to get natural gas. Helium is not necessarily a byproduct, but helium is gathered during this process. And you can see on the map on the right side of the slide that dark area is really where most of the helium stores in the United States happen to fall. Now, there is a global shortage of helium. In the United States, that area is really all that we're getting as far as helium is concerned. And the U.S. Strategic Helium Reserve is expected to be closed to commercial sales in 2021, which makes helium price go even higher because now there's more of a demand. People want to get it ahead of time. And what's more is when we are doing scientific applications, we do require a high purity. So all of these things in combination with each other is really what's driving the cost up. If we take a look at the graph in the bottom right of the slide, you can see that in about 20 years, the price of helium has doubled. And this is simply because we are, quote unquote, running out. We don't have a way to generate helium on Earth. If you look up to the sun, actually, we see the nuclear fusion of hydrogen going to helium, and that's lovely, but down on Earth, we can't actually do that because of the activation energy for this process. So ultimately, what our customers are telling us is they either can't get the helium or they're being severely delayed in receiving helium from the vendors. And actually here at Shimadzu, that's no exception to the rule. We also are kind of being moderated on how much helium we can get here at the corporate office. Now, before we dive headfirst in talking about changing carrier gas, let's first talk about conserving helium if that is the gas that you have to use. For example, we do have some industries and some folks from companies out there that call us and they say, look, I'm not allowed to change from helium because if I do, it's going to require revalidation of my method, and based upon my facility requirements and the regulation body that oversees our operation, we would have to stick with helium in the short term. So, all right, let's talk about conserving the helium if that is something that you have to do. Now, my first recommendation is to use the carrier gas saver mode when you're setting up your method. This is particularly important with large split ratios because ultimately what the split ratio is doing is it's helping to concentrate a smaller amount of sample onto the column for separation, and the rest of it kind of just gets blown out the split vent. The larger that split ratio, the more the split vent is open, and therefore the more gas we are wasting during the run itself. So what I like to do is I like to turn the gas saver mode on. You'll notice on the image on the right, I have the carrier gas saver mode on, a split ratio set to 5, and the time set to 1 minute. The reason that I've set the time to 1 minute is because at 1 minute I have nothing coming out. I would want to make sure that I set the time prior to whatever analytes are coming out of my column. And secondly, I'd want to set a split ratio no less than 5. Once we go less than 5, then the precision of how much the split vent should be open starts to get a little bit more questionable. And secondly, what I would recommend is when you are closing up shop, so to speak, at the end of the night, you should stop your GC after the usage. So basically what you should do is set your carrier flow to end mode, and ultimately that will turn off the carrier flow on your GC. And I do want you to be mindful that if you are using one of the Shimadzu GC 2010s, 2010 pluses, or 2030s, they do have automated flow controllers on their detector gases. But if you're using the GC 2014 and haven't added an automated flow controller, just be mindful that your gases would continue to run even though your carrier gas is shut off. And this is particularly important if your makeup gas actually is helium. So just be mindful of that as well. Now, hydrogen probably is the best alternative to helium, but people are hesitant to use hydrogen because it is an explosive gas. The biggest hesitation probably is stemming from the Hindenburg explosion, which took place in New Jersey in 1937. Ultimately, there was a plan to use large blimps like the Hindenburg for commercial travel, but when actually it exploded, that was kind of the end of that thought process. So other hesitations to using hydrogen would be detector sensitivity. The GCMS is not as sensitive when hydrogen carrier gas is being used, and that's because the outlet pressure coming from the column is a bit higher, and so therefore it takes the vacuum a little bit harder to pump down in that environment, making it a little less sensitive. And then also the GC FID, if you're using FID as your detector, you're adding fuel to your flame by using hydrogen as your carrier, and ultimately that does kind of make a little bit wonky of a flame, and so therefore it's not as uniform as we'd like it to be. That does have a little implication on the sensitivity. And lastly, hydrogen is a reducing agent. There are a couple examples of compounds that could be reduced. The most notable probably would be the nitro compounds. If your compound does have a nitro group in it and it goes into the ion source of the GCMS, it would be reduced to an amine. So just be mindful of that. So continuing on with the discussion of hydrogen safety, hydrogen is only combustible above 4% by volume in air. Now, if your FID flame were to go out, hydrogen would be pumping into your lab room. But if you were to take your lab room and split it up into 100 slices, 4 of those slices would have to be completely hydrogen in order for this to combust, which isn't realistic. Our flows that are coming out of our column and also the flows that are being used to fuel the FID are so low, and also the HVAC system that's in your room and the hoods are going to prevent that from ever approaching 4%. Now, if we think about the oven, however, the oven is a small space, and what's more is it's small heated space. Now, if hydrogen were to enter the oven, it probably wouldn't take very long in order for the oven to fill with hydrogen, at least to the 4% threshold. Maybe from a leak in the column or a break at the end of the column, and that's something that we would worry about. So I do want you to be mindful that we do sell hydrogen sensors for your instrument that would give a warning at 1% by volume, and ultimately shut down your instrument at 2% by volume if you didn't heed that warning. The other thing of note is to make sure that you're not using copper tubing. Hydrogen ultimately makes copper tubing brittle, and it could break over time. So we want to prevent that from happening, so then we don't actually get large flow rates of hydrogen going into your room. Our customers sometimes ask if nitrogen would be feasible as an alternative to helium, and the answer to that would be yes, but I do want to take a couple of considerations. The first thing to note is that nitrogen is only optimal at low linear velocities. The plot on the left is the Van Deemter plot for carrier gases, and what I want you to note is on the y-axis we have HETP, which stands for height equivalent of theoretical plates. Ultimately, what we're looking for is that number to be the smallest possible. When that number is smallest possible, it means that the separation is going to be the most efficient. You can see that the nitrogen curve is optimal at 10 centimeters a second linear velocity. Now that's quite slow, and that causes a couple things to happen. Number one, your run times are going to be longer, and number two, you are going to have a little bit more eddy diffusion taking place inside of the column. Ultimately, the peaks are going to be broader. If we take a look at hydrogen, hydrogen is very broad peak. And what that means is by moving either higher or lower on that Van Deemter plot, you're not really going to compromise as much efficiency in comparison to nitrogen, which is quite steep. So ultimately, nitrogen carrier, even though you'll notice that the low point of that curve is the lowest, it does give the best efficiency, but it is unforgiving if you veer away from the optimal linear velocity. And hydrogen carrier is optimized at high linear velocities, and the deviation from optimal has minor impact. Ultimately, the way that I like to put this is faster linear velocity means faster analysis, and as we all know, time equals money. So if we really break this down, looking at helium, the pros of helium is that the published methods, historical published methods, most often use helium, which is great because it doesn't require us to revalidate a method for changing our hydrogen or changing to hydrogen gas. The optimal separation is at a fast linear velocity for helium, as according to the Van Deemter plot that we looked at on the last slide, and the small atomic size prevents interference with sample. Basically, this prevents the sample from diffusing, as we see a larger impact with nitrogen. The cons, however, is that it isn't very available. There's no way to create it on Earth because of that activation energy that we discussed, and also it's very expensive. So if we have a look at hydrogen, the pros are that it's abundant and it can be generated. We could use a hydrogen generator, which will do electrolysis of water to give us that hydrogen gas. Hydrogen's inexpensive. You have an optimal separation at faster linear velocities, even in comparison to helium. The small molecular size prevents interference with sample on hydrogen, as it does with helium, so this is a pro for both of them. The cons is that it's explosive, and I did put that asterisk there just so we could talk about how to prevent it from being explosive by using that hydrogen sensor. It's also going to have impacts on our sensitivity, and it also is a reducing agent. So if we have a molecule that could be reduced, that is a consideration that we should take. Okay, so if you've decided to switch from helium to hydrogen, I just want to make a few notes when you're doing this change on how to make sure that you have successful chromatography. The first thing that you should consider is that you need to change your instrument system configuration for the injection port to indicate that hydrogen is being used as your carrier gas. The reason being is because the gas is only monitored in the injection port with regard to its pressure. So if I were going to use constant linear velocity, there's actually no mechanism that's being used in order to gauge what is the linear velocity of my gas. It's all based upon pressure. And so there's an algorithm that your software will use that will calculate what pressure needs to be maintained, or basically what pressure needs to be input into the injection port in order to maintain a constant linear velocity. Now, because hydrogen has a different density than helium, that is important. You do have to enter that into your instrument configuration. Secondly, perform inlet maintenance and consider changing the gas filters on the GC. Now, the inlet maintenance, we're going to make sure that it is conducive to your sample. Basically, if your sample has sulfurs in it, you want to make sure that it's self-inert, and so you might need to do something with regard to your injection port there. Now, really, the major consideration here is the gas filters. Hydrogen gas often contains moisture, and this is true about tank hydrogen gas as well as generator hydrogen gas. And also, light hydrocarbons are often found in tank hydrogen gas. So if we could put some filters on there, that would make us have a less wonky baseline if we're using that as a fuel for the FID. And then also, it would make sure that there's a minor impact on your chromatography if you're using hydrogen as a carrier gas. Lastly, consider using a tapered inlet liner to improve the performance. Ultimately, because hydrogen molecules are a little bit on the small side, we do want to help our sample get onto the column, and so having a tapered liner does help with sample focusing. So customers ask, where do I start? How do I make sure that my method using hydrogen is going to give me the same result that my method using helium will give? And the answer is, this is a good question because the density and the viscosity of hydrogen is different than that of helium, and so therefore you would expect there to be different chromatography if you were to keep everything the same. In order to accommodate for these changes, there is a valuable tool from ResTech's website called EasyGC, and it allows for the quick and accurate conversion of methods between carrier gases. Now, be mindful that this is kind of an estimation. It's just a tool to get you started. Other translation modes such as translate or efficiency might improve your chromatography, and also, in my experience, I have had to tweak a few things here in order to get something that actually does give me baseline resolve separation. The thing that I do want to point out with this method translator is that the oven program temperatures will remain unchanged. So basically the starting temperature and the ultimate final temperature will remain unchanged. Only the ramp rate and hold times are modified, so just be mindful of that. So a couple slides back, I did mention that your GC is monitoring only the head pressure. And so you have to make sure that your carrier gas type and column dimensions are entered properly in order to make sure that the linear velocity and the flow of your gases are calculated accurately. So if we're considering the control modes, then we have constant pressure, constant flow, constant linear velocity are our choices. And if you were to do an isothermal run, isothermal analysis, all of these three control modes would work the exact same way. Now, the consideration really is if we're doing a temperature ramp. So for me, because the linear velocity is directly correlated to the separation efficiency, as according to the Van Deemter plot that we've discussed, I like to make sure that I'm using a constant linear velocity mode. If I were to choose constant pressure mode and increase my temperature, as you can see on the top left graph, if I were to use constant pressure and increase my temperature, I would notice that the linear velocity starts to go down, down, down. Now, the implications that that has is it would veer away from the most efficient separation. It would veer from that optimal linear velocity. So I do like to keep it on constant linear velocity mode in order to do my analyses. So I've mentioned the Van Deemter plot a couple times already, and so I really want to show some chromatography that really will drive this point home. So on all three of these chromatograms, I'm using helium carrier gas, but I'm changing only the linear velocity. So if I'm using as according to the top chromatogram, a 10 centimeter per second linear velocity, there's no surprise here that the analysis is going to take longer, ultimately because the analytes are traveling slower through the column. No surprise. But helium is not optimal at 10 centimeters a second. So our R value, which is talking about our resolution, is 1.23. This leaves a little to be desired because it's thought that R value of 1.52 is truly baseline separation. Now, if we look at the 20 centimeters a second, we start to see that the R value goes up. The analysis time gets shorter. And then 40 centimeters per second, which is actually closest to the helium optimal linear velocity with regard to these three numbers, gives us the best resolution and also the shortest analysis time. Okay, so in these three chromatograms, what I'm doing is changing the carrier gas, but they're all set to 35 centimeters per second. If we take a look at nitrogen on the Van Deemter plot, 35 centimeters per second is far outside of the window of what happens to be the most optimal linear velocity for this carrier gas. And so it's no surprise that our resolution is the least of these three carrier gases. And the other thing I want you really to take a look at, and I could have done a better job of making it really stand out here, but if you look at the peak width, look at the peak width in the blue chromatography, you can see that at the base of each of those peaks, it starts to become broader. Now this broader is going to decrease my resolution because this is where I start to have peaks run into each other. Now because this resolution is above a 1.52, it is thought to be baseline resolved, and so we have no issue here. But I do want you to be mindful that we do start to see that peak broadening when we start to use nitrogen. And if we look at helium and hydrogen, where 35 centimeters per second is pretty much optimal for these carrier gases, you can see that the resolution for both of these carrier gases are much better than nitrogen was, and still much better than the 1.52 resolution that we're really looking for. This has to do mostly with gas density and gas viscosity. So these two gases compare really well when we're comparing the three here. So now that we talked about the theory behind using hydrogen as an alternative to helium, I really want to show you some good data that was collected. So I will be showing you a FAME application, and then when I pass it over to Rick is going to talk about a couple of the applications that he's done on GCMS. So for my FAME application, I did this with FID, and it's according to published AOAC method 996.06. Now, what FAMEs are, they're fatty acid methyl esters, and the reason that industry uses this is because people like to know on the back of their food label how much of their food how much of their food is saturated fat, how much of it is trans fat. And then I show you a couple of these fats here. We show you the saturated fat at the top, the trans fat in the middle, and then the cis fat on the bottom. Now the saturated fat and the trans fat, people don't like those in their diets because they stack really nicely. And since they stack really nicely, it means that they have a higher melting point, which means that in the body it is more likely that these would be solid, solid enough basically to clog your arteries. So people try to avoid saturated and trans fats for this reason. Now, AOAC method 996.06 does require the user to turn the fatty acids, which start as a carboxylic acid, into a FAME, a fatty acid methyl ester. And this is just for column compatibility. Basically, if we leave it as a carboxylic acid, then it does eat away at the mobile phase, the stationary phase of the column. And also it does lead to very, very broad peaks. And so when we turn this into a methyl ester, we don't end up having this problem when we're trying to get quality chromatography for this application. So some of the things that analysts really are looking for when they're looking at their chromatography to determine if it was good is something that we've already talked about, resolution. So if we have a resolution of 1.52 or above, it's considered to be baseline resolved, and this is really the cream of the crop. This is what we're looking for in chromatography, because then we don't have to make assumptions about peak shape continuing on, as it being Gaussian. The other consideration that really is that we're going to have a look at here is the LOD, LOQ information, and this is just the limit of detection or limit of quantitation. Really the limit of quantitation is what I'm interested in, because I'd like to quantify how much FAMEs are in my food samples. Now, this is all based upon the signal-to-noise ratio. So basically, the better the signal-to-noise ratio, the better the LOQ. Now, this has two considerations, right? The signal, do I have a very good signal, or do I have very good noise, or do I have both or neither? And this is something that's really going to come into play as our discussion goes on. For me, the hydrogen carrier gas, as we'll see, has a greater implication on the noise, not so much on the signal. The other two considerations are the linearity of a calibration curve that's being used, and also the repeatability. What's the percent RSD of the area for each of the peaks? Now, these considerations more so rely on the injector and the detector being quality and set to performance standards, but they do have a little bit of implications with regard to carrier gas, so I have included them in this presentation as well. So when I used AOAC method 996.06 with its parameters as published, I wanted to point out a couple things that I was running into as problems. So on the top chromatogram, you'll see where I have the word coelution, and underneath of it, I really zoom in on those areas. The two peaks on the left, you can see actually they don't go all the way down to the baseline, and the resolution values for that would have proven the same. The other thing is that tall peak on the right-hand side actually is supposed to be two peaks. This is a 37 component mixture, and that peak actually accounts for two analytes that are hidden under the peak. So as we can see, the AOAC method 996.06 as published didn't work out here, and it needed a little tweaking. A couple of things that I wanted to point out is I had to presume that they held something constant. And the AOAC method does use a temperature ramp. So this method was updated in the early 2000s, between 2000 and 2010. And so because of that, I assumed that they wouldn't have used constant pressure here because they're using a temperature ramp and it wouldn't make sense. I assumed to use constant linear velocity just because, in my opinion, it is the best mode. And the thing I do want to point out is the AOAC method uses helium carrier gas at 18 centimeters per second for linear velocity, which I found to be a little strange. That's not its optimal value. But I didn't write the method, and so there must be some reason that that linear velocity was chosen. I went ahead and ran it. I got the coelution that I pointed out. And the other thing I want to point out is this runtime. This runtime exceeds 65 minutes, and nobody likes runtimes this long. So one of my challenges, or one of the things that I really wanted to do with this AOAC method, is to see if I could still get the same quality chromatography by shortening that runtime just a little bit. And I'll talk about how I did that. So in order to get the AOAC method to actually give me the separation that I was looking for, such that it would separate into 37 different components, I did have to tweak the carrier gas linear velocity, but everything else is consistent with what AOAC method does recommend. And so here, I'm using a constant linear velocity mode at 24 centimeters a second, as opposed to what they published to be 18 centimeters a second. So I did have to toy around with this value in order to get quality separation. Now, I did want to keep the hydrogen as close to the AOAC method as I could, just so we could compare apples to apples. I did have to drop down on the linear velocity just a little bit and went down to 22 centimeters a second, just so I could make sure that the separation was consistent with that of helium. One thing I do want to point out is I did say in the last slide about method development and making these runs a little bit shorter. You can see in the early part of the run that those peaks are very well separated. The AOAC method starts the oven temperature at 100 Celsius, but maybe if we were to start the temperature a little bit higher, we could take advantage of that resolution in the early part of the run, squeeze that a little bit together such that they're not co-eluting, and that way we could shorten the run for this purpose. So this is the data actually that was generated from the chromatography that we saw in the last slide. Remember, I did have to change the helium linear velocity from the 18 centimeters per second that AOAC publishes to the 24 centimeters per second to get it some good separation there. And if we take a look at the resolution, we'll notice that all of the peaks, with the exception of peak 32, is above that 1.52 quote-unquote baseline resolution requirement that we need there. If we look at the signal-to-noise ratios, they're all above 400, which is good. And so now let's have a look at hydrogen. Hydrogen resolutions, all of them are above 1.52. Remember, I did have to back off on the linear velocity down to 22 centimeters per second, but I'm really trying to compare apples to apples here and make sure everything is as consistent as it could possibly be without sacrificing the resolution. The signal-to-noise here, you'll notice, is a little bit lower, though. We are at all above 300s, which is a nice signal-to-noise to have. I do see a 200 there on number 30 and 32, and that's okay. But the thing that I do want to point out is, why do we think that the signal-to-noise of helium is greater than that of hydrogen? And as I mentioned earlier on, if we're using hydrogen carrier gas, which also happens to be the fuel for the flame of the FID, then we are adding a little bit extra fuel to the flame, meaning that the flame is going to not be as stable. So really, the consideration here is that changing to hydrogen carrier gas has an implication on the noise more so than it does on the signal. So instead of showing you 37 different calibration curves that we could use in order to compare the data that was collected from helium to the data collected from hydrogen, I've selected one peak here, peak 19, which happens to be about midway through the run, that we could do some comparison on. And then I just wanted to point out that the R-square values with regard to linearity on all of the other peaks are above 0.997, which is quite good. And the area percent RSD is below 4%, with most of them being below 3%. I do want to point out that a long analysis time and a low boiling point solvent does lead to an increased percent RSD with regard to the area, and that is common for this type of analysis. So here, if we're looking at peak 19, the linearity here has an R-squared value of 0.9986, and so on. So this is quite good with regard to linearity. Now remember, linearity isn't as much implicated by the carrier gas as it is by the injection port and the strength of the detector. But I did want to include that here just so we could discuss it. The other thing is that the percent RSD with regard to area, or the reproducibility here, is looking really good. So in this case, if we look at the different concentration levels, the 20 ppm level has a percent RSD of 1.375. 10 ppm has 1.302, if I were to round up. 5 ppm is 1.213. 2 ppm is 1.618. And 1 ppm is 0.115. So those percent RSDs are actually quite good with respect to this peak coming out. the thing that I want to take most note of, because this is what's going to change the most between hydrogen and helium, is that LOQ value. If we look at that LOQ value, then it says that the limit of quantitation when using helium is 0.0163 ppm with regard to these standards. So we'll really pay attention to that number when we look at it in comparison to hydrogen. So looking at peak 19 with our hydrogen data, all R-square values again are above 0.997, and all area percent RSDs above 1 ppm are less than 6% with most below 4%. So we do see a little bit of an increase on the percent RSDs here. Remember, I said that the noise is probably the most implicating factor here. But what I do want to point out is on those concentration levels, the 1 ppm level has a percent RSD above 6.8, which is quite bad. If we actually were going to do some data analysis on this, some LOQ values, we would see that anything below 1.14 ppm cannot be accurately quantitated. And so the fact that the 1 ppm standard has such a bad percent RSD, there's no problem here. It's not a surprise because the LOQ suggests that anything below that value can't be accurately quantitated, and so therefore we do expect to see those numbers to vary by a great deal. So we've seen with regard to sensitivity that helium is a little bit better here, right? But everything's a trade-off. Now, if you need your if you need to quantitate values as low as 1 ppm, then maybe you would have to stick with helium. But if anything above 2 ppm was fine for what you're looking for, then switching to hydrogen here would have no, negative impact. Now, the other thing that we talked about early on is that hydrogen is a reducing agent. And so I wanted to make sure that my unsaturated bonds were not turned into saturated bonds throughout the process. Now, if we think back to our organic 1, catalytic hydrogenation is a process that is very common, and usually it's better when a palladium or a platinum catalyst is used so that we can lower that transition state. And so that's what I'm showing here on this energy diagram. But we don't have any platinum or palladium in our column, so the hope is that that transition state is at high enough energy to where that reaction does not take place. If I were to take the ratio of 14 carbon chain completely saturated in comparison to the 14 carbon chain with 1 double bond, and look at that ratio with helium and hydrogen, they end up being about the same, which means that the ratio hasn't changed, and so therefore conversion hasn't happened either. So that's really what we're going with here. 15 carbon chain in comparison to a 15 carbon chain with 1 double bond, again, we can look at that ratio and see that there's no change there. And so because there's no change, we would say that the conversion of the unsaturated bonds to the saturated bonds isn't happening. In other words, there's no reduction, or there's no evidence of reduction taking place, at least for these samples, for these FAME samples in the FID. So earlier on, I did allude to making the AOAC method a little faster. We were at 65 minutes for the method using 18 centimeters a second for the constant linear velocity for helium, and I wanted to make that shorter because, remember, we said time is money. So if we switch to hydrogen carrier, the benefits of this is, number one, it's cheaper than helium, and secondly, as far as analysis time is concerned, it is higher efficiency at faster linear velocities. In other words, we get a better separation when it's faster, and so therefore we can also capitalize on the we could also decrease that dead time early on in the run in order to make these runs quicker. Now, the temperature program is somewhere else that we could look in order to make this analysis go by quicker. If we started at a higher column temperature, then remember that resolution early on in the run, we could take advantage of that having very good resolution, kind of squeeze those peaks together a little bit, and then not have any problem with regard to our separation. Now, the reason that I really wanted to do this is because a customer had reached out to me to ask me to help them with their method development. And so ultimately, they have found that this is leading to lower cost of gases and an increased throughput. Ultimately, their company is making better revenue. And so here I wanted to show you the changes that I've made to the chromatography from earlier on. Here we have a dead time of 5 minutes. Earlier runs we had a dead time of 10 minutes, and this is an artifact of me increasing the linear velocity. And I was able to do that again because I'm using hydrogen, which is optimal at higher linear velocities. Also, the resolution here, I maintain the resolution that I did from earlier runs. I was able to separate all of the 37 components, and the run time was able to be shrunk in half. And so this is really an accomplishment here because now we are getting double the throughput that we were able to do previously while still getting the same exact information. And I know we're all for happy endings, but unfortunately here, as we've seen before, the hydrogen does leave a little bit to be desired with regard to the LOQ, even of the faster hydrogen method that I just showed you. So the reproducibility at 10 ppm is that top graph. You can see that those peaks sit very nicely right on top of each other. They don't change with regard to area or peak height very much. In the chromatogram slice that I show you below, though, that's at 1 ppm. Take a look at all of the variation with regard to those peaks. So again, any LOQ below 1.58 ppm here is not going to show me what I need to know. And so therefore, if you are looking at sub-ppm levels, then maybe switching to hydrogen for the FAME application isn't for you. But most people, especially with regard to FAME, aren't looking at that low of a concentration, so there would be no negative implication for using hydrogen if you were going to look at LOQs above 2 ppm. So I would like to just hone in on some of the things that I discussed with regard to my application before I toss it over to Rick. The conclusions here on the FAME application with FID is that we were able to provide quality, linearity, and reproducibility for the FAME analysis using AOAC method 996.06. This is not a surprise here. Remember, this really isn't talking too much about the carrier gas. But it is financially beneficial to switch to hydrogen, and it does not exhibit any evidence of reduction chemistry with regard to unsaturated FAMEs, which is, I think, a home run there. Hydrogen carrier falls short at low-level concentrations using the modified method, and in this case, the LOQ was just under 2 ppm, and the expedited method, and it was under 0.02 ppm using helium carrier. So it really depends on what you're looking for. Everything in chromatography is a trade-off, and so if you can sacrifice a little bit of sensitivity in order to save money in the long run using hydrogen carrier, then that might be something that you'd be interested in exploring. Although a cheaper alternative to helium, hydrogen carrier does not provide the same sensitivity and linearity as helium, and so this is something to be mindful of when you are considering a switch with your FID. All right, Rick, you're up.
We have seen data on how switching from helium to hydrogen affects gas chromatography using standard GC detectors, but what about mass spectrometers? Switching from helium to hydrogen has many of the same benefits with GCMS as we see in GC. The retention times are reduced due to the increased linear velocity used for optimal column efficiency, which therefore gives higher sample throughput, as you can see in this slide here for some pesticide analysis. How does the data compare between helium and hydrogen carrier gas? There is typically some loss in peak area, usually around 20 to 40% depending on the application, but the peaks are typically sharper and the baseline noise lower with hydrogen, so sensitivity loss is around 20% with a typical pesticide run. Also keep in mind that precise method development regarding column flows and temperatures can improve this somewhat. Here we see a depiction of the reduced retention times and comparable calibration curve linearity for some selected pesticides. The retention times are 80% of helium using hydrogen with similar resolution, and the linearity is very comparable to what can be achieved using helium. What about reproducibility? With 6 replicates of a pesticide sample using hydrogen, we can achieve below 5% relative standard deviation for most analytes, with very consistent retention times as well, as shown in this slide. This indicates that the hydrogen generator is delivering a stable, constant flow of hydrogen to the GC. Switching to another analysis, this being the determination of aromatics in gasoline, we see that we achieved reduced retention times for the analysis without any reduction in analyte separation. The run is reduced from 32 minutes for helium down to 21 minutes for hydrogen, significantly increasing sample throughput. For this analysis, the peak areas are reduced much less than is typical between helium and hydrogen, no worse than 80% peak area for hydrogen versus helium. This method calls for a minimum acceptable R-squared linearity of 0.99 for all analytes, which both helium and hydrogen carrier gas can easily achieve. The example calibration curves for toluene show that hydrogen performs just as well as helium for this application.
Thank you, both Kyle and Rick, for speaking about hydrogen versus helium, some of the safety concerns, the chromatographic considerations, as well as some of the tips and tricks that may make your switch a little bit easier. Now we're going to shift gears a little bit and hear from our special guest, Ed Connor. Ed Connor is product manager at Peak Scientific, and he will be phoning in from the Philippines to give us a little bit more information on the pros of using a hydrogen generator. Go ahead and take it away, Ed.
Okay, thanks for the introduction, Alan. So, as Alan said, I will be giving you an overview of gas generators with some particular focus on hydrogen. And as a starting point, I thought I would just give you an introduction to how they function for those of you who are perhaps not familiar with this technology. So a gas generator produces ultra-high purity gas from compressed air or from water in the case of a hydrogen generator. So on the left you can see we have a figure showing how nitrogen produces or is produced from compressed air via a process called pressure swing adsorption. And what happens here is we pressurize the column of carbon molecular sieve material, and it will bind oxygen and allow nitrogen to pass through. And so what we can do is just keep repeating this process until we end up with very high purities of 595 for GC applications. Then if we look at hydrogen production, this is different. It's not produced from air, of course. In this case, we're producing hydrogen from deionized water. And we use a thing called a PEM cell, a proton exchange membrane cell. And by applying an electrical charge to the cell, we can dissociate water into its constituent hydrogen and oxygen atoms. And these will produce hydrogen and oxygen molecules. And we vent the oxygen away and retain the hydrogen to supply to the application. So this could be used for GC detector or also for carrier gas. And then we also have zero air generators, which would be used typically in an FID detector for flame support. And in the zero air generator, we are taking compressed air and we are removing the methane from this. So we're removing hydrocarbons to give us a flatter baseline so that we can do better trace analysis in GC. And this process occurs where we will combine oxygen with methane and convert this to CO2 and moisture. Now, when we look at generators as a device that's used in the lab, one of the primary reasons that people will tend to opt to purchase a generator rather than use tanks or dewars is gas safety. And tanks and dewars contain high pressure gas and also high volumes of gas, which can be a danger to lab staff. So if we look at a typical 50-litre tank, this will contain around 9,000 litres of compressed gas, and the pressure can be up to 20 bar in a typical cylinder used in a lab. And then again, if we look at nitrogen dewars, so liquid nitrogen dewars, 1 litre of liquid nitrogen will expand to almost 700 litres of gas. So if you've recently done any health and safety courses, I'm sure that this will have been something that was highlighted during the course, because there is a risk of asphyxiation. And often there's a lot more focus on hydrogen and other flammable or explosive gases like acetylene, but you have to remember that nitrogen and other inert gases also pose a risk in terms of asphyxiation risk, rather than the risk of a fire or explosion, but they can be extremely dangerous. And so generators in general produce enough gas to support an application. They provide the right grade of gas, but they do operate at a low pressure, and there is a low volume of gas stored within the generator. So if we now specifically look at hydrogen versus cylinders or tanks, one of the key things with hydrogen is that below a level of 4.1%, it is actually not going to cause a risk of fire or explosion. So this is the key threshold at which there is a potential danger to the environment. And so we normally work with this lower explosion level of 4.1% to assess whether there's a risk from a gas supply. So if we take the example of a fairly small lab, or maybe average size, 5 meters by 4 meters with 2.5 meter room height, we have a total room volume of 50 cubic meters. So in this case, the lower explosion level to reach the lower explosion level of 4.1%, we would require just over 2,000 litres of hydrogen. So if we are supplying hydrogen from a tank, we would need just around 1/4 of a tank to reach the LEL in this case. So you can see why there's now more regulation on tanks and more requirement to move them out of the lab space, because a quite significant leak from a tank can quickly mean that you reach the LEL. Now, if we contrast this with a gas generator, so for example we have a gas generator that produces 1.2 litres per minute of gas. At any time this generator actually contains less than 300 cc's of gas throughout the system at a pressure of just under 7 bar. So if we compare the cylinder with the generator, you can see why generators are preferred as the safer choice of gas supply. So in general terms, the reasons that we would invest in a gas generator are really the main 5 points on the slide here. So as I've already mentioned in some detail, safety, because we're looking at a device that provides enough gas for your application, but at much lower pressure and with fail-safe features in place. We also get consistent performance from a generator, so we're not going to see the potential variation that we sometimes see when we supply from tanks. Also, if we look at gases like hydrogen, from a generator, this is hydrocarbon free, so again, you're not going to need to worry about the purity of the gas that you're receiving and the potential effects it's going to have on your results. And by having a generator which is providing gas around the clock, you're also not having to break the connection between your GC and your gas supply, which again will reduce the risk of introducing impurities into the system. Then convenience is also a key benefit of a generator. So as I mentioned just a second ago, you have round-the-clock supply. So as long as you have a supply of electricity, and in the case of a hydrogen generator, you will also need deionized water. You will have gas round the clock, 24/7, 365 days a year, which means you don't have to worry about whether that tank is going to run out over the weekend if you set the autosampler up before you leave. We can also sometimes see cost savings. So one of the benefits of hydrogen as a carrier gas is that you can run your samples faster. And so for anyone who works in a contract lab, there's a potential benefit of being able to run more samples per hour and generating more revenue through using a generator. And there's also a low ongoing cost. Once you've invested in the generator, we're typically looking at annual filter changes. And then finally, the environment is also, of course, an important factor that needs to be considered. And when we look at repeated deliveries of cylinders or tanks, then these are normally brought in by truck. And so the effect on the atmosphere of the emissions from the trucks is also something to bear in mind, compared with a device that once delivered to your lab will remain on site for the time that it's operational. Now on to GC performance. Of course, if you're on this webinar, I'm sure you're interested in how your GCs could potentially be run using alternative carrier gases such as hydrogen. Now, it's important to mention that you're not always going to be able to switch your method from helium to hydrogen. So one of the first things that is worth looking into is looking at where you can conserve helium for methods where it's essential to use helium, and then potentially looking at moving other methods that are not as critical or are not regulated in the same way to hydrogen or possibly nitrogen. So there are simple things like looking to make sure that you're using the gas saver option on your methods. But then do look at your method and see whether there is scope to change to an alternative carrier. One of the benefits of changing to hydrogen from helium is that you have the potential to improve the chromatography of your method. So actually using hydrogen means that you will potentially be able to run your carrier gas at a higher linear velocity without sacrificing the separation of your peaks. And this is obviously highly advantageous to labs where they're particularly under time pressure to get samples turned around, as I mentioned in the last slide. So contract labs in particular may be interested in this, but any lab that's under time pressure may want to investigate the benefits of using hydrogen carrier gas. And of course, by supplying it from a generator, you have a safe, consistent supply. And there is a real opportunity if you're supplying a lab with multiple detectors and also for carrier gas to reduce your operational costs by investing in gas generators. Now there's an increasing amount of information out there about switching carrier gas. We have information on the Peak website. I've got the URL from Shimadzu's website there as well. So there's plenty of information. I would recommend just doing a lot of research before you actually make the change. But of course, if you have any questions, then there are experts at both Shimadzu and at Peak who would be able to discuss with you if you need more information on this.
Well, Ed, thank you so much for your presentation, and we appreciate you taking the time to do so. Now it's going to be time for questions. It seems like we have a bunch rolling in regarding some hydrogen generator questions. So I figured since Ed here is calling in from the Philippines, we'll go ahead and knock those out first. And let me just go ahead and grab that first question that I saw because I think it's a pretty good question. Let's see. How many instruments can one generator supply?
Okay, thanks. Yes, so really it will depend on what you're using the generator for. So if you're just using it for detector supply, so if we take hydrogen as an example for an FID, we're usually looking at around 40 cc's per minute for each FID detector. So basically it would just come down to how many detectors you need to supply. We have a 1.2 litre generator, so for larger labs that could actually support up to around 30 detectors. If you're using the generator for carrier gas supply, then it would be a case of looking at your total carrier flow and then adding that to any additional detector flows you have, and then just making sure that you're slightly below the capacity of the generator. But we have generators across the whole range of flow rates, so we should have something for more or less any lab.
Oh, perfect, perfect. Thank you. So the next question that I see here is, what type of water is typically used with a hydrogen generator? Can I use tap water?
Right, yeah. I think a lot of people would like to do that. Unfortunately, we can't recommend that you use tap water or river water or any other kind of natural source of water. What you actually need is deionized water. So this would need to be a water from like a Millicue system or an Elga type system, and the ASTM rating of that water would be type 2. So it's less than 1 microsiemen or greater than 1 megaohm resistivity. So that basically is needed to protect the cell in the hydrogen generator to make sure that continues to work properly and produce good quality hydrogen.
Okay, perfect. Thank you. And then one final hydrogen generator question for you. What type of maintenance parts and pieces or consumables can I expect when using a hydrogen generator?
Okay, yeah, so this is actually, I think hopefully people will be quite happy with this answer. There's very little to do in terms of maintenance. You need to change one component every year, that is the deionizer cartridge, and so that again is another safeguard that we have to protect the cell. So basically all the water that's being supplied to the cell goes through the deionizer cartridge to scrub any additional ions from the water that can build up over time. And then in addition to that, if you get a generator that is designed to supply detector gas, then often these have a desiccant dryer, and that will periodically need to be changed out. For carrier grade gas, we actually have a regenerative dryer, so the only maintenance on the carrier grade generator is the deionizer cartridge once per year.
Wow.
Hopefully that answers the question.
Yeah, absolutely. That's plenty of information. Thank you. I appreciate that. So I see where we have a question more in regards to a specific sampling technique. This question is, can I use hydrogen as a pressurization gas for my headspace analysis? Rick, why don't you take this one?
The answer to that question is absolutely not. Pressurizing hydrogen in a vial is a bomb. In essence, it's explosive, so we don't want to do that. You can use hydrogen as carrier gas for your GC when you're doing headspace analysis. You just cannot use it as the pressurization gas.
Perfect. Awesome. Thank you. And it looks like we have another situation with a different detector here. I know we talked about FIDs in the presentation, but this question is, what if I'm running an SCD in my lab? Is hydrogen as a carrier gas suitable for my lab? Kyle, do you want to take this one?
Yeah, so Shimadzu sells a bunch of different detectors, and so I get this question a lot as far as like what detectors are compatible with hydrogen and which aren't. And so since this viewer is asking specifically about SCD, I'll entertain that question to start. And the answer to that really is part of the mechanism that the SCD is using in order to identify the sulfur compounds is an oxidation step followed by a reduction step. So actually some of the detector gases that you have to use are oxygen and hydrogen. Now if you are using hydrogen carrier, you actually won't get complete oxidation of your compounds, and so it no longer would work as a linear equimolar detector. So in this case, no, you would not be able to use hydrogen carrier, but you still would have to have the hydrogen as the reduction gas, as part of the SCD system.
Okay, thank you. Let's see here. Here's one. Okay, here, let's get one more in line with mass spec. All right, Rick, this one's going to be for you. Does hydrogen carrier gas affect the mass spectral information, fragmentation, things like that?
There have been studies on that question, and the answer to the question is it does not significantly affect the mass spectra that are generated when using hydrogen and carrier gas versus helium. So you will have no issues with getting good spectral matches with your analytes.
Perfect. Okay. And it looks like we're running a little short on time, so this is going to be our last and final question. And I think this is a good one because it doesn't necessarily pertain to hydrogen or anything as a carrier gas. And Kyle, I'll let you take this one. The question is there a difference between nitrogen and helium as a makeup gas?
Okay, so I guess this question is being asked really because this lab is trying to phase completely away from helium. Presumably, I guess this user is using helium as their makeup gas, and they're interested in getting rid of helium, so probably. The answer to this really is helium has been shown to give you better linearity with regard to calibration data when used as a makeup gas, and nitrogen has been shown to give better sensitivity actually. You get better LOQs when you are using nitrogen as a makeup gas, and really, I don't want to go too far into the theory of this, but really the purpose of the makeup gas is kind of to help keep the flame, uniform throughout the run, and basically help to propel the analytes from the tip of the capillary column into the flame. And those, without getting too far into the weeds, the answer really would be nitrogen would give you better sensitivity. You might just sacrifice a little bit of your linearity there.
Perfect. Thank you. All right. Unfortunately, we have run out of time. Thank you all for those who have submitted the questions. I apologize if we did not get to your questions. However, don't worry. All of the questions that you submitted in the Q&A box will be sent to us via email, and you should receive a response answering your question within the next few business days. Again, we appreciate you taking the time to ask those questions. Sorry we couldn't get to those, and we shall get back to you with an answer as promptly as possible. Thanks so much. So one last time, thank you Rick, Kyle, and Ed for your responses as well as your work on preparing this webinar. With that, our webinar has concluded, and I'd like to thank each and every one of you for joining us today. All of these webinars can be accessed on Shimadzu's website at any time with no expiration date. All you need to do is register for the webinar, and it will be available on demand at Shimadzu's website. Also, be on the lookout for more webinars we look forward to sharing in the future. One more time, all of the available resources on the page can be downloaded at any time as well. Slides, links to manufacturer sites, as well as app notes and data can be downloaded at any time. Hope you have a great day, and thanks for joining us.